Hello and welcome to this episode about the amazing properties of wires. The format of this video will be a bit different this time. This is going to be more like a traditional presentation, and yeah, I'm really interested in hearing your comments on how do you like this video and this format, and if you have some topics for the future videos as well, please leave your comments down below. But now let's see how interesting the wires actually are and what kind of things they have that we don't necessarily think on our daily lives. Here's a rough outline for the presentation. First of all, we will have a look into different kinds of wires and their properties, how do they differ, and what kind of wires there are altogether. Then we will discuss shortly on the speed of electricity and also on the speed of electrons in this context. And that will take us to the transmission lines, where we will discuss about the transmission of power from one place to the other. And we will also have a look on a practical lab example on how the signal propagates along the wire. And in the end, I have provided some links which are also used in this presentation. Yeah, as we all know, we are surrounded by wires. They are practically everywhere. If you go outside, you can see these power lines there. Inside our buildings, we have the electricity built into the walls, and we may have all sorts of consumer electronics with wires, and you have the USB cables, and you have power cables for your devices and whatnot. The wires, they come in all sizes, all shapes, all colors. Here we have some inductor wires, and we have some jumper wires for the breadboards, and flat cables, and audio cables, and coaxial cables of different kinds, and yeah, we have power cables. This is a short, by no means complete list of different kinds of cables, but something to give you an idea of the variation and the terminology. A cable that refers to multiple insulated wires within a jacket. A coaxial cable is one example of those. It's a cable where an inner conductor is surrounded by a conducting shield. We will discuss about the coaxial cables soon. A flat cable, it's a multiple insulated wires attached side by side so that they form a flat ribbon. Then we have those printed circuit board traces, which are conductive parts on the circuit boards. Stranded wires are number of small wires bundled or wrapped together for an enhanced flexibility. And then we have twisted pair, a cable construct where wire pairs are twisted together for a better electromagnetic compatibility. So basically you have two wires twisted together. And the wire itself, it's a single conductor. Yeah, the coaxial cables consist of a core wire. You have this inner core, which is surrounded by an inner dielectric insulator. You can maybe see it in this connector or in those connectors. It's the white stuff there. A conducting shield on these adapters and connectors. It's the outer part, which is the conducting shield, but in here it's beneath this protecting outer shield. I have few formulas in this presentation, but they are only here to capture the core concepts and how they are related. We don't have to focus too much on the math and the physics in here. what comes to this characteristic impedance in coaxial cables, one important thing is that we can approximate it on the basis of the tons of the cable and the capacitance of the cable. So it's the ratio and the balance between them. We don't have to consider the resistance too much if the length of the cable is reasonably short. And another important thing is that the impedance is dependent on the dimensions of the inner core and the outer core. So basically, how much this what's the width of this dielectric insulator in between, and that also already just suggests the fact that the signal propagates in this space in between those two conductors. And if you take this idea further, there are those waveguides which are used for microwaves especially. Basically they are, then you omit this inner core and you have a conductive tube, and the microwave propagates within this tube. And even further, if we go to higher frequencies, for example to the visible light or something close to that, we can have those optical fibers, and then you don't even have the conductive shield, but you have these total internal reflections on the outer surface of the fiber. Then what are the wires and what kind of properties they have? Of course, the first thing that comes to mind is probably that they are conductors. So charge carriers are transferred along the wires. They are also typically somewhat resistive. Some energy is dissipated as heat, except in superconductors. Sometimes the heat is exactly what you want, for example, if it's a heater. They act as antennas, and in principle, antennas are some kind of wires. Unshielded wires can be used to transmit and receive electromagnetic radiation. Of course, they also behave like capacitors, at least to some extent. Wires store tiny charges, and their parasitic capacitance can be seen in many sensitive high-frequency applications. We will come to these Smith diagrams later on, but for example, in here you can see that this coaxial cable of 1 meter behaves like 110 picofarad capacitor for the 30 megahertz frequency. Inductors, yeah, as you can see in here, they are pretty much wires wrapped around something. A magnetic field forms around a conducting wire and it stores some energy there. Of course, all wires, they have the physical, mechanical properties. The mechanical strength of a wire can be used for various applications. And of course, there are many other aspects of the wires. They take some volume and so forth. One may consider many linear components, special wires in special configuration, emphasizing some of the intended properties. That's especially true for capacitors, inductors, maybe for antennas. They are, in essence, some kind of wires. They may be made really flat and close together, or they may have a particular length to behave as an antenna and so forth. Of course, in order to use wires, you have to connect them somewhere. And in the end of the wires, unless they are soldered somewhere, you find connectors there. Connectors are used to form strong, solderless, and often detachable joints. Prevent unintended miswiring. That's why we have such a huge variety of different kind of connectors. So you don't accidentally, or not that easily accidentally, miswire your things. The connector itself is a good indicator for the purpose of the wire. Ground connection is emphasized in many cable connectors. It typically connects first and disconnects last. That's often a safety feature, and then it also shields the inner wires from the external noise. Then small connectors are typical for high frequency applications, as they tend to have less parasitic capacitance. For example, if you have coaxial cables, you may have smaller connectors for higher frequencies, and then you may have, for example, these PNCs for lower frequencies. Metal fatigue is something that you have to consider when connecting cables. Metal wires and their connection points especially are prone for fractures when bended. Stranded wires are more resistant against the metal fatigue than typical solid wires. Vibrating or moving wires shall not be soldered. So they tend to break down right after the soldering point, because it becomes really hard from the solder, and then after that part it tends to break. Clamp connectors are more resistant and can be used there. A connector can be followed by a sleeve for some extra support. That's typically what we see right after the connectors. You have these small short sleeves there. Some of the properties of the wires include temperature range for operation. It's an interval for the lower and the highest temperature. Of course, often we use Celsius or Fahrenheit units, although the Kelvins are the SI unit. The elasticity, especially for, say, you have a computer mouse with a wire, then it's good to have an elastic wire there. You may have your test probes, for example. On the other hand, a more rigid wire or cable may be used for some structural support. The colors, they often play an important role to distinguish between wires. They may also tell something about the role of the wire. For example, the ground or the live or the neutral wires may have their own colors, so that they are not that easy to confuse. Especially on the outdoor solutions, the ultraviolet resistance and the durability of the wires or cables is an important factor. Many properties are somehow proportional or dependent on the length of the cable. For example, the mass, the longer the cable, the higher the total mass. The same holds for the resistance, or its inverse, the conductance. The longer the cable, the more resistance you build. The impedance and the admittance, you can have larger charges, on parasitic charges, or larger electric field around the longer wire, and of course, the longer the cable, the more it typically costs. The cross-sectional area, the standard unit, here's a reference for the standard, is of course the square meters, but also these American wire gauge measures are widely used in practice. The skin effect relates to the alternating current. So here we have like an example of cross section of a round wire, and the current density of an alternating current tends to form an exponentially decreasing gradient towards the depth of the conductor. So you have a higher conductivity, or more of the current flows here on the outer surface, and less current flows here in the depletion zone. The skin depth, this small delta, represents the depth where the current density drops below 37%. Again, a formula, but now the important point is that the skin depth is dependent on the frequency. So the higher the frequency, the thinner the skin depth. Again, it's also dependent on the permeability of the material, but of course the wires are typically either copper or aluminium or similar metals, so the permeability doesn't vary that much between the wires. The conductivity of the material is one factor. It's not necessarily that intuitive, but the more conductive the material, the thinner the skin effect is. Although it would be easier to flow here in the middle, but actually the thin layer is enough to conduct that. And the skin effect makes the signal losses frequency dependent. That's something to keep in mind for complex waveforms. A quick recapture on impedance, just to revise these concepts, because we will face these quite many times in this presentation. The impedance is the total opposition to alternating current. The unit is ohm, which we all know from the resistance. Resistance means energy loss as heat, and that's independent of the frequency. But then there are these reactive components. No energy is lost through the reactance. Reactance consists of capacitive reactance and inductive reactance, and the net balance between them determines whether we speak about inductive reactance, and that's when the inductive reactance dominates it, and the reactance has a positive value. Then it's purely resistive. Here's a mistake. When the inductance is 0, that should be equal, and the capacitive reactance is when the net reactance is negative. One notion in here about this complex representation of the impedance is that, we have the resistive part and then the reactance part, but this imaginary symbol is often J in electronics, where we typically use lowercase I in math, but that's just to avoid confusion to the current symbol. As we have this complex representation, we can plot these reactance values on 2D, and now basically one dot or point in this graph represents the impedance at certain frequency, and the reactance is on the y-axis and the resistance is on x-axis, and then you can plot the behavior of your circuit or your system on various frequencies. Now if we have the constant resistance but the varying reactance, we have these vertical lines, and on the other hand, if the reactance is constant in here, but the resistance has different values for the different frequencies, then you have these horizontal lines. If they are above the 0, then we talk about inductive reactance, and below the 0 we have the capacitive reactance. Now, if we bend this a bit, this graph, we end up having Smith diagram. You can see that now this vertical constant resistant curve makes a circle in here. These Smith diagrams are often calibrated for some nominal impedance. In here we have one, but that could be, for example, 50 for typical 50 ohm coaxial cable, or say 75 ohms or so. And now we can plot different frequencies on here and see how the total impedance behaves and how it's constituted from the resistance and the reactance. We will see examples later on where this makes sense, because the frequencies, it actually often makes these circles, and that all comes to those wavelengths. Speed of electricity. Electronic signals propagate approximately at half of the speed of the light in vacuum along the PCB traces. That's a rough measure and varies, of course, but you can see that the speed of the electricity in these media is slower than in vacuum. You may think that the speed is so fast, and if those PCBs are of the size of few centimeters, that it doesn't really matter. The signal propagates instantly from one place to the other. But actually, contemporary systems have such a high frequencies that these speeds do matter. For instance, 25 picoseconds tolerance between signal requires matching below 4 millimeters, and that's something that you will face in contemporary systems. For some DDM memory traces, you may need matching length to 0.5 millimeters even, so half a millimeter differences may distort your signal. Here we see these weekly lines, which are here to match the length of different traces, so that the signal arrives at in sync to the load. So even if the path has a different route, they all preserve the length of the route. You have those curves all over the PCB. Even if this electromagnetic field propagates at the speed of light, the actual movement of those charged particles is amazingly slow. The average movement of the charged particles is called drift velocity. That's of course proportional to current. The faster they move, of course, the more current moves there. That's proportional to the strength of the electric field in resistive materials. So yeah, that's again quite intuitive for the relationship between the current and the voltage. Electrons move randomly in the absence of an electric field, so the net drift velocity is 0. If there's no electric field, there's no net current either. The drift velocity is in a 2 millimeters diameter copper wire in 1 amp current is roughly 8 centimeters per hour. So that's not much. And then if we think about alternative current, that's again a bit different. Back and forth movement in alternating current, and that's why there's no net movement practically. They may vibrate those charged particles within few micrometers. They are practically at the same place. Veritasium published an interesting YouTube video a while ago. He introduced an interesting setup to demonstrate how the signal propagates within an electrical circuit. I have a link in here for the video, and we will have a look on that later on. Here we represent a somewhat simplified setup along the same idea. How long does it take for a signal to reach our voltmeter in here once we press the button in here? So we can assume that this power source and the switch are on the other side of the voltmeter. We have this 1 meter in between, and then we have this really long wire between the switch and the voltmeter. The length of the wire is so long that it takes 1 second for the signal to reach the voltmeter, and the same holds for the other side of the circuit. So it takes 1 second for the signal to travel this part. So we assume either that the velocity factor is 1, or then if it's less, then that would be a bit shorter this wire, so that it takes like one second to travel this. If the velocity factor would be 1, then that's roughly 300,000 kilometers long wire. Option A is that it takes roughly 1 second, travel a half circuit from the switch to voltmeter. So the electricity goes from here to here, and then we have the response. Option B, it takes 2 seconds to complete the whole circuit back to the battery or to the switch, if we assume that they are practically at the same place. Or then it takes 1 divided by C, so basically immediate response, what it takes from signal to propagate this 1 meter or reach over this gap between the wires. In case A, the full voltage will be reached as the current completes the half circuit. So that's in a way correct. You can see the response in here as the signal propagates all the way in here. You can see that of course sooner than completing, because it doesn't really affect. As long as the potential in here is lower than in here, then you have the voltage difference. So you don't have to wait until it gets back in here. But interestingly, you will see a tiny decrease in voltage already after 1 divided by C time here, because this will behave like an antenna. So the electric field that you build in here as the signal starts to propagate will induce a reverse current in here, and basically you will see this current on this wire as well. It's not comparable to what kind of voltage you will build once the signal reaches this end, but there's something there already. Transmission lines. Here's the symbol. It resembles this coaxial setup a bit, if you will. The transmission lines, they are to transmit power from source to load. So that's their purpose. Why we talk about transmission lines is that in the context of alternating current, it's important to consider those waves. And the theory becomes important as the length of the wire exceeds, well, this is a rough estimate, but it's good to consider these wave theory and the transmission line theory if you are at the order of 1/20th of the length of the wavelength. So depending on the higher the frequency, the shorter transmission lines become significant. Transmission lines behave capacitively on low frequencies, but then as the frequency increases, then these inductive impedances become a significant part of that. An open wire acts like a short circuit when its length is exactly wavelength divided by 4, or its odd multiple. And this is something not necessarily that intuitive. If you have just a coaxial cable and then you have the length of the cable is a multiple of the wavelength divided by 4, it actually seems like a sorted circle, although there's nothing there, just open end. And we will have a practical example of this later on. Next, the following vector network analyzer examples are produced by measuring those S11 reflections of an unconnected coaxial cable. So now we have a coaxial cable, and then we vary the frequency, and we are measuring just one end from which we also send the pulses in. That's why we have the port 1 and port 1 for the signal and the measurement. And here's the condition we have. So now we have this Schmidt diagram in here, and we are looking on this green curve. So now each point in here represents different frequency. We are looking at here where we have this 1. This point represents 97 megahertz frequency. We can see that the impedance of this wire, we have roughly 1 meter of coaxial cable there, and the impedance is 1.41 kilo ohms on this frequency. But then if we move to here, now the frequency is 48.52 megahertz, and the impedance has dropped to 1.12 ohms. So it's roughly 1,000 of what we saw in here. So in a way, this is closed circuit in here, and then here it was almost open. Well, not really open, but 1.4 kilo ohms. Here's a transmission line equivalent circuit. You can imagine that this coaxial line, for instance, is an infinite series of blocks of this kind, where we have an inductor, then we have a series resistor in here, then in parallel to the outer shield we have a capacitor and then a parallel resistor in here. And these resistors, they basically represent those losses, signal losses along the line. We can imagine this is an infinite series of these blocks. We have another one in here and yet another one, and there would be infinite number of those until you reach the load. The total resistance of these series and these parallel resistors is typically so small that we can ignore them, and we can simplify the model like this. And now we have this purely reactive simplification where these inductors, they represent the magnetic field built around the wire, and then there's this capacitive coupling towards the shielding. The velocity factor tells how quickly signal propagates along the transmission line in respect to the speed of light in vacuum. Velocity factor of a typical coaxial cable varies between 86%, which is, for example, gas-injected foam high-density polyethylene cable, and 66% for a solid polyethylene dielectric. And there are more statistics on this in Wikipedia if you are interested in. The reflections. There's some variation in impedance along the transmission line or your circuit path. The improper impedance matching causes these reflections. A square wave includes high-frequency components, and the frequency-specific properties of the transmission line will cause a distorted signal. Then we can have a look on these in practical examples. Later on, we can see how an open circuit where we had this cable without any termination, you get the reflection back. Then if you short the other end, you get this closed wire loop, and then you have the inverse reflection. And then if you have some kind of attenuation there, that can be used to control the reflections. We will demonstrate these soon in practice. Then how to do this impedance matching. That's important. So we want to avoid the reflectances in order to have the maximal power transfer, and that was the purpose of the transmission lines. Also, those reflections, they may distort your signal, and the system may actually misbehave or doesn't work at all if you have too bad reflections there. So one option is that you have lossy matching, and that can be achieved with a resistive network. So basically you can build voltage dividers. They are frequency independent. That's a clear advantage, but of course they consume some energy from the system, and the reactive impedance needs to be insignificantly low, so they don't work for reactive impedances. Reactive matching is more efficient because then you don't lose the energy. Frequency-specific solutions with a limited bandwidth, so you can build low-pass or band-pass filters there, or high-pass in order to control the reflections. You may use impedance matching transformers. That's quite typical solutions. And you can use those mid charts to design the matching network. Again, here's a link for different kind of transmission line matches. Here's one example from the signal generator. We have 50 ohms output, and then these oscilloscope inputs are 1 mega ohms. And now if you would connect these 50 ohms output impedances directly to this 1 mega ohm input impedances, you would get clear reflections from here unless you terminate the signal in here. And then how to do the termination. One option is to use, for example, now for these lab equipments, to use these terminators. they are used in the end of the transmission line when the impedance of the load is above the transmission line. Simple resistor in parallel to the load, so they are not too complicated often. You may have seen these on the old Ethernet networks even. So years back, the computers were connected from one to the other, those networks, using coaxial cables, and then you had these terminators in the end of the cable there. And properly terminated transmission line behaves like a pure resistive load without capacitance. Okay, let's have a look on how these things that we've been discussing can be seen in practice. Take a long cable for a reasonable delay between the test pulse and its reflections. So it has to be long enough that we can measure the input pulse and distinguish from the reflection that propagates later on from there. And then you can connect your cable to a signal generator which generates short pulses with reasonable voltages. In our case, we are using 32.6 nanosecond pulses of 6 volts peak to peak. The other end of the cable is left open for the following experiments. It's in here, but we will have a better look on that next. Connect an oscilloscope probe to the input side of the cable and use input pulses for the triggering. Here we have a better picture of the test setup. Here is the open end. This is not a coaxial cable in this case, because I just happen to have a cable of, I think there are 5 wires inside. And we are now using 2 of those. I didn't have that long coaxial cable at hand. But what we have on the other side, we have the signal generator. We've connected those 2 wires on this end. The other one now represents the outer shield, and the other one is the inner core. They like represent those. We've divided this signal also to the oscilloscope in here. So we have this split. So the oscilloscope is measuring what's going in and or the signal at the same place as it's delivered and received from the wire. Here's the open circuit condition. So these are not connected from the other end, and we have the input pulse, and then it takes 95 nanoseconds to see the reflection back. So it goes there to this end and then goes back, and you can see it 95 nanoseconds later. Of course, there's some attenuation. Some of this can be explained also by the other reflection from this end, because those are so overlapping. Then I've connected or sorted these wires by adding this alligator clip between them, and now you can see that there's the reverse reflection. The time delay is of course the same because the length of the cable is identical. It's just that now as the signal goes in here, it continues the other end, but now the relative potential difference between the cables is inversed, because if the signal goes in here, it continues here, then the voltage is higher on this side in respect to that one, and now we have the reverse signal. The last example is in here. Now I've added just a small, I think this is 40 7 ohms, if I recall correctly, resistor in here. I haven't soldered it in here, and of course this is not a proper 50 ohms coaxial either, so I haven't measured what's the impedance of the wire at now, but anyway, it seems that it works fairly well. Of course, you could still improve, but if that was the original reflection, now we've really reduced the height of the inverse reflection in here. So if you adjust your termination properly, you can get rid of those reflections altogether. That's all for now. Thank you for listening so far. I still have these references for you if you want to look further information about these topics. We had this standard for those insulated cables, and they measures. I've been using these 2 books of the Art of Electronics, 3rd edition. There's this X chapters extension to this book series, also used. Then we had this Veritasium's excellent and really interesting YouTube video, and there are also many follow-ups. For example, Alpha Phoenix prepared a nice experiment where he demonstrated this concept on the field setting. Then, if you are interested in those transmission line matching and impedance matching, there's an excellent link for that topic. And of course, Wikipedia provides all sorts of important resources, like there's an article about the speed of electricity and the velocity factors. All these slides or the source codes for these later slides can be found online from my GitHub repository. And yeah, please subscribe to my channel for more videos on electronics. We'll see you on the next video. Thank you very much. Bye bye.